All right, let's go. Let's see if this works. I haven't been streaming in a while, so sorry for the delay. Yep. All right. I haven't been streaming in a while, so sorry for the confusion. Can you hear me well? Is the sound okay? Because, yeah, I have been messing around with my settings and it seems to be a little bit shaky. Also, I don't know if the resolution is fine. I should be streaming in high resolution, but I have my test view here to the side, which kind of looks pixely. I don't get it. All right. Okay, so actually 1080p seems to work. Yeah, perfect. Awesome. All right. I've been thinking about streaming a bit about nMigen or nMigen a few times. Haven't really done anything lately, but recently I just got some idea to implement some crypto algorithms. So yesterday I implemented Sha-256, which was quite fun. And so today I'm thinking of implementing Sha-256 because, you know, hashing, why not? It's fun. So my environment is kind of, yeah, tailored for myself. So I'm not sure if it will be readable on stream. I tried to get the GTK wave working with bigger font size. I'm still struggling because I guess you cannot really read the hex values that we have over here, right? It's all kind of super tiny, right? Oh yeah, let's increase that a little bit. So I guess you can maybe read that. All right. Maybe, yeah, there was some setting for the GTK GTK wave, right? Oh, crap. Yeah, let me just see if I can fix that. Where are you from? Yeah, from Sweden. So I hope you can understand me. I have some dialect, of course, but yeah, hope it's understandable. Okay, let's see if I can fix the font. Thanks. Okay, one more time. Nope. Why is it always... this is the stuff that I should have prepared before. Let's see if I can do like this instead. Okay, one more time. Oh, here we go. This is perfect. Yeah, this is... now it's almost too big. But yeah, this should definitely be good enough for streaming, right? Yeah, maybe it's even a little bit too big. Let's use 12 perhaps. Yeah, perfect. All right, so let's begin. So welcome to the stream, and thanks for bearing with me. Today I want to implement SHA-256, a common hash algorithm that you find being used in many places. You might want to slightly increase the editor font size. Okay. Let's do that. It's gonna get a little bit cramped here. I'm probably gonna move this one over to a separate screen. Yeah, let's do that instead. Okay, here we go. So, where should we start? Let's start with what is SHA-256? It's a hash algorithm, and we should probably be able to find a reference implementation in C and be able to port that over to nMigen. That should be fine. So yeah, I guess text meshing, you've been recently poking around with this algorithm, right? So I wonder what would be the best way to approach this. So I guess just taking a reference implementation and converting it. I needed it for my very profitable Game Boy Bitcoin mining project. Yeah, exactly. So let's see if we can do better in nMigen, just for for fun. Okay, let's just look up a nice SHA-256C implementation. See if we can find someone who wrote something nice, easily understandable. Yeah, here's just some rotation macros. This would be super easy to do in hardware. Some logic, also easy. Some rotations, shifts. So these things are super easy to do in hardware, and you can hook it up so it's happening immediately. Then here we have some constants. All right, and here we have some, yeah. So here we do this 64 times, and there's a lot of iterations going on here. So I guess let's start with the state machine approach, where we essentially implement the algorithm almost like a CPU, but we can do a little bit more for each step. So yeah, where should we start? So the way you use this is, if I remember correctly, you initialize a state, and then you update it with each block of data that you have. And then finally you do a final round, which gives you the output. So I think this code was actually very nice to read and very clear. So let's use that. Yeah. So let's just do like this. Like so. So my idea is that I should be able to add some nice debug prints that we can, like we splice up the algorithm into different stages, and then we can dump the registers or states in each, during the development while we are working on it. So yeah, let's get started. So let's start off with just compiling this. I guess we need a main function to test it out. Let's see here what's happening. Okay, cool. So we need a context, and then we should initialize it. And then we can start off with not updating it. So that we get the initial hash. Oops. Oh, hi. Hi, Geek at Work. So yeah, today we're implementing Is Sha-256 in nMigen. So I'm starting off with basing it off C implementation, and yeah, let's just continue on from there. Try to split it up into different stages and see where it takes us. So there was even a test here. That was convenient. Yeah, let's just get this one as well. Okay, so it seems to at least run. Okay, so yeah, let's remove the space. So the idea here is that we are testing that this is our hash with this program, and this is the hash of an empty file using the established SHA-256 sum program. So this is just establishing a baseline. Now we know that this code works. Oh, right. Maybe you can't see the lower part of my screen. Let's fix that. Maybe like this. Yeah, should be fine. Okay, so now we have a starting point. So let's just look at the primitives. What do we have? How does it work? So we have this context, which contains 64 bytes of data, and a state, which is 8 32-bit unsigned values. Good afternoon. Yeah, so let's set up our project. So so our starting point is basically this. We are importing everything from nMigen, and then we should create a class. So this will be the class that handles this. I usually never write everything from scratch. I usually just base it off something else. But yeah, what you need is an init function. Where you can set up signals that are going in and out of the module. And then you have this elaboratable or elaborate function. So this is the function that generates the logic. So yeah, let's just make something simple, and we can go through every step. So I have this project called Pergola, which is a FPGA board, and I have this Pergola project's Python project, which is a framework around applets and gateware that lets you compile and use various IP logic. So there is DVI-D and a bunch of different things. So it's just my playground basically, where I do stuff and try it out. So I usually set it up using a test case using the built-in Python unit test framework. And then there's an extension here which is based on the built-in unit tests that gives you some extra stuff, especially useful for formal verification and stuff like that. But we don't have to do that now. So let's just start with something simple. Right. So in a unit test, we usually need some sort of test function. So let's call this something. Yeah. We need some simulation stuff. So again, since I'm quite a lazy person, I just usually build upon something that I've done before. So we need a module which will contain our logic. So we will do something like this. So basically, we need to instantiate the class that we're testing. So what we're doing here is we create a test module, and we instantiate the module we are testing. And then finally, we are going to actually test this module, and we're going to run it. And to do that, we need a simulator. And the simulator is, all right, we need to import that. So it's a built-in feature in nMigen where you are able to, with Python, execute the HDL. So let's copy some more code. So you need this function called process, or I'm not sure if it needs to be called that. No. So basically, this is the most simple test case you can do. So we have a module that doesn't do anything. We have a test module. We instantiate the module we're testing. We're creating a simulator. We're telling it to run at 1 megahertz. We do nothing for 1 clock cycle, and we are simulating it, and we are executing this and exporting the output to test.vcd. So let's just try this. Right. Okay, it failed. Yeah, I guess we need to do something. Okay, here we go. Right, so let's open this up in GTK Wave. Okay, it actually managed to load it. So here we have our awesome test. So we have our clock that ticks for each iteration. And then we have our foo variable or signal, call it whatever, which we are toggling. And yeah, that's basically it. This is our test case. Perfect. So now it's time to create some structure. Now we have a baseline. So just a second. Okay, so if we go back to the C program, we had the structure of this context where we have data and state. So let's just try to understand what the role of data is here. So it's reading data and it's writing to data in this place here, and it's actually overwriting data here. Okay. I'm just thinking if we need data to be sort of mutable, or if it can be like an input read-only thing. But here it seems that we're actually overwriting it. So I suppose we actually need an internal data copy. So yeah, let's do that. So if I understand the algorithm correctly, so the data is ordinary bytes, but the most of the operations seem to be working on there's like a mix of 32 and 8-bit stuff going on. I'm just thinking what would be the most sane way to have it internally. Okay, so maybe this time we should have an array of. So again, I'm mostly fumbling around in the dark, but hopefully learning something in the process. So we need a way to represent our input data and also operate on it. So I'm not sure if we should have a list of bytes or if we should have an array. Maybe an array would make more sense. Yeah, we can change that later. So let's start with creating. How much was it? 64 bytes, right? Yeah. So I like to keep an IPython console open so that I can try out stuff while developing. So, right, something is wrong. Right. So this yeah, looks sane. Now we have an array of bytes and 64 times. and then we need a state, which was 32-bit, and if I don't misremember, it should be in big endian. nMigen is not too friendly for tinkering in REPL, I find, but oh well. Yeah, you're right. But at least I can sort of try something, see what happens. So how much did we need here? I think it was 8, right? Yeah, correct. So yeah, how do we want to continue? Should we look at the I guess we should have an output hash as well. So could have it like this, and then is it 64? Yeah, it is, right? No, it's 32 actually. Okay. So our output hash is 32 bytes. Okay. What more do we need? I mean, the data will be sort of updated. I guess we need a signal to tell it when we are done, so that you first initialize it, and then you give it data, and then you process the data, and then you give it more data, and you do this until you have hashed everything you want, and then you finalize it. So I guess, yeah, I don't know really. What would be a sane way to do this? Maybe some sort of strobe. Data ready. Or something. So we need a state machine. I always forget this. State, right, makes sense. So we only start from an idle state where we don't do anything. If something happens, for example, data ready, we should continue on to the next state. What do we want to do in the init state? I guess we want to prepare what we're doing here. So there are some magic values here. The question is if they should be in big or little endian. Well, I guess we'll find out. Oh, shit. Okay, now we have some magic values. Nice. Now what? So I guess this should always be done when you're starting on a new hash. Mm. So maybe I should actually move this up here. So yeah, I guess that makes sense. So we're always starting off with a clean state. And then we can go to an update state. Right, so we start off with this initial state. And then whenever the user is signaling data is ready, we move on to the update state. So, okay, how does that work then? So we can just skip this for now to make things easier. So after the update state, however that should work, we want to go to some sort of processing state. I guess that's called the final stage. And what does that do? That does a bunch of stuff. This was kind of new to me. So it's padding the data with OX80 for some reason. And then 0 bytes. Okay. Okay, so datalen never actually I'm trying to understand what this code does. Okay. Yeah, I don't think we need to care about this right now. Okay, now I get it. So whenever you call update, it only calls the transformation function when you reach 64 bytes. So if there is some data left in the buffer, it gets padded and then transformed. Yeah, according to the schema. Okay. So it does the last transformation, it seems. In either case, like even if there is data left or if there is no data left. So actually, this is kind of, I don't really get this. Like it seems to always encode the size in the last 8 bytes. Right. Okay. Yeah, so this is something that we don't need to do. We don't need to swap the NDNs because we are operating in big endian. All right. So what does it do with the hash? It simply outputs the state. Okay. So that means that this should be extremely simple for us to do with the initial state. Should basically just be outputting this, right? Oh, am I missing something? All right, it is actually doing, so this is a critical step, I guess. So even with an empty hash, we are going through the transformation step. Yep. So let's implement that. So in our case, since our data length is 0, all of this should basically be on the initial context or initial state. Yeah. Okay, so let's implement this one then. So this is where all the magic is happening. So let's try to understand how it works. So it uses the 32-bit word for everything, it seems. It loads up a 64-word large array called M. It converts the data into big endian words. Yep. And then already here, we are operating on on M. So it's performing this rotation and shift. In this way. So yeah, I guess we need to do that. Then it prepares some stuff here, loads the state into variables. Then it does a bunch of stuff. And then finally it saves the state. Okay. What about the constants? It's the k. So where is k being used? It's being used here. Okay. So, okay. I guess as a first step, we can implement until this point, perhaps, and see how it looks. Okay, so these are the values of m at this point. So let's implement this in hardware and see if we can get the same values. And I think these will be in little endian. They will be printed in little endian, but they should be in big endian on our side. So yeah, let's start. So I guess we can call this the transform step. Okay, so what do we need to do? First, they are loading up the data, basically just interpreting it as words. And yeah, I mean, this is going to be a waste to do like that, but we can do that. This is quite big, 64 32-bit values. That's a lot of resources, but yeah, let's do it. So first we just copy it like this. Yeah, we can do that. I'm sure there is a nicer way to do this, but let's just do it like this. Gonna rename this a little bit. Oops. Okay, so what I'm doing here is that I'm creating an array of statements that will update the M array with the index of I, which we're looping. All right, this is not gonna work. Let's do like so. So data is in bytes, right? And M is in words. Is this? It's looping 16 times. Okay. Yeah, but that makes sense. Yep. So in our case, I is the J variable. Yeah, exactly. So yeah, but that makes sense. So I should do like so. Yeah. No, I'm stupid. Right. So M0 up until 15. Yeah, will be populated with the data. Yeah, but this should be fine. This should be fine. So we can do it like this. But it should all be zeros. No, maybe I messed up. Oh, right. So it's actually changing the data here. Ah. Okay, I guess I'm gonna have to do everything after all. So I suppose I mean, the data length should be 0, but I suppose this is, I need to debug this and to, okay. So it is really just OX80 in the beginning. Okay. Oh, now I get what's. So the reason I was confused is because this is a stack variable, or it's allocated on the stack, and they're only initializing the first 16 entries. That's why I got this junk data that I couldn't really explain. Okay. Well, now at least that is sorted out. So let's just let's just do like this instead. Yeah, this looks much better. And here we have the OX80 in the beginning and zeros for the rest. Okay, that makes sense. Perfect. Okay. Let's do this properly later, but for now, let's just do data 0 equals OX80. So we get this one. And then we can do the transformation step. Cool. Yeah, so what we need to do is we need to tell the module that the data is ready in order to start off the processing. So let's do that. Now it looks a little bit different. So now suddenly we got a bunch of signals. And here's the state machine. We see we are in the idle state. Data ready goes high, but nothing is happening. Okay, so why is that? Because I'm doing this completely wrong. I think this is all right. No, that's how you do it. Okay. So here I'm telling the module that it should start, but for some reason it doesn't really do anything. Oh, right. I made the mistake. So this is a huge... No. Sorry. I thought I made a mistake because it's very easy to forget the D here when you're doing the m.d.sync and so on. I thought that was the case here. But actually, when you're changing states in the state machine, that is how you do it. You set m.next. Oh, right. That's that's actually... Oh, God. Here we go. Yeah, here we go. So now we can see that the state is actually changing from idle to update to final to transform, which is the expected state transitions. Perfect. So let me just explain my mistake. So when you're changing states in the state machine, you set m.next, or the module instance .next. You can call this anything, but m is a very common way to do it. So I did like this, m.state equals, which, yeah, I don't know why I did it, but it was wrong. So this is the way you should do it. Perfect. So now we can continue. So in order to inspect this one, I'm gonna move this up here, like so, and then m equals self.m. This way, this array will be visible in the yeah, in this view. I think maybe it gets pruned away. Also, it seems that we're losing our names. Maybe it's a property of the arrays that the names disappear. Not sure. Let's see if this makes it more readable. Yeah, this makes it way more readable. So it seems that when you're creating like anonymous signals, they get very anonymous names. Usually they get a name based on the variable name, but because I'm doing this in a sort of loop, I guess the name disappears. It cannot really understand what I want to call it. So that's why I'm doing like this instead, setting the name explicitly. All right. So yeah, let's see if our M contains the OX80. It does not. Oh, it does. It's just really hard to see. So, all right, I should start this with a bigger font size. Didn't I manage to get the font bigger? Let's do 20 again. Yeah, this is better. So let's scroll down. Yeah, so here you see that we have our OX80. Perfect. Okay, so what do we want to do now? Let's move on to the next step. So again, this is in little endian notation, and this is in big endian. And this always trips up my brain. But hopefully this will be fine. Okay, so let's convert these into Python. I guess this might become a huge brain breaker for me. Because since this is written in C for little endian machines, I have no idea if this is gonna work in big endian. Crap. I guess this algorithm is a little bit too much to do in a stream because I kind of need peace to think, and I always get a little bit stressed out. I don't know, but yeah, we can try. We can try. So, if I'm reading this correctly, we're operating on the unchanged x multiple times. So that should be fine. So yeah, let's do like this: x dot rotate hmm, just creating the next step here. I just want my editor to cooperate here a little bit. Nope. Okay, here we go. Rotate right 17 XOR rotate right 19 and then should take the whole x and shift it right by 10 without wrapping. Okay. So what we're doing here is that we are writing back in the next clock cycle a new value for x, the input. So, oh, wait a minute, maybe we can't do this. Okay, I'm gonna return it as an expression instead. Yeah. So, okay. So because this is hardware and kind of, as a software person, kind of weird to wrap my head around. This is an expression that is operating on an input. Right now, nothing has been written anywhere. It's just an expression. It's just a chain of logic. If you implemented sig1 and oh, thanks. So I guess we can do both of them. So rotate right 7, 18, and 3. Now we have both of them. So again, we are returning an expression. Now we need to do something with this. Yeah, thanks. And now we are going to do this. So how do we do this in a sane way? Let's do something similar as the loop we did above. So we are going to write back to mi, just like we did here. And this time, let's do like this. It will loop 64 times because the length of m is 64. We have 64 words, if you remember. And then instead of doing this, we are going to have an expression, right? We want to copy this whole expression. Now the question is, this addition might overflow. And when you do expressions like this, they will end up as temporary signals with more bits than you have in your signals, I think. So for example, if you do, yeah, I mean, this thing is something I'm not really sure about. Like for example, if you have a 1-bit variable or 1-bit signal, and you do a plus b, what do you get? You get an expression that is adding these two. And if we have something, a 2-bit variable called c, and we do something like this, then essentially this will handle the carry. And I'm afraid that this will produce a carry instead of overflowing. Is there any reason you can't do the transform 1 in the same cycle? Data not ready. It doesn't affect the same array elements. Oh yeah. Yeah, probably. I'm just. I think I will just do it in a stupid way first, and then do it smarter later on. Like this whole step is probably not really needed at all. You can probably do that somewhere else. Yeah. Anyway, let's just try to figure out this addition with carry and see if we can figure it out. So maybe I can create a convenience function that is so we want to add one thing with another, but we want it to overflow, right? So instead of just truncating like this, I don't know if this will work. So honestly, I'm gonna try this. Let's try it here. And do like this. And then Let's skip this for now. Okay, it seems to actually work. So, okay, so what I'm doing here is that I am creating two signals with 32 bits. I have some reset values, and then I add them together, and just confirming if it overflows correctly or not. And here it seems to overflow just fine. But if you have like a bigger expression like here, I'm worried that it might not really work. But yeah, maybe it's not a problem then. Okay, so let's rename the M to uppercase M because M is already taken. And I messed up somewhere. Okay, so I'm missing something. I'm blind. So let's just say oh, thanks. Yes, you're right. Right. This is the simple case. And then we can put the complicated logic instead of I here. And then we can replace the M's with the uppercase M's. Yeah, okay. So now we get a different error. Shouldn't have, thanks for the follows. I'm missing one required positional argument X. Okay. Oh, right. Since I'm not using M, it's just an expression. I don't need the M. Right. This should work. Okay, okay. Back in business. Okay, that was just me being slightly confused. So now we have replicated this for loop in nMigen. So let's try it out. So we can simulate it. We can run GCC. We want this here. We need a few more cycles, I suppose. Oh, right. We shouldn't look too much. Okay, so something seems off. Shouldn't this be 64? Uppercase M. Okay, it's the So this sometimes happens if you're not using all of your what's it called again, signals. They are not even being created, so it gets optimized away. But yeah, here it seems we're back in business, so we should look at the state. Yeah, so this is the inside of the transform state. We have loaded the OX80 here, and then one cycle later we are operating on it. So this looks not really right. So we are probably missing something. If we look at the C code again, we are doing this 64 times. I minus 2, I minus 7. Oh, wait a minute. I is 16 here. Ah, okay, right. It's always fun with code that is not immediately understandable, but yeah. Yeah, you see here is 16. So yeah, that's maybe that's yeah, Jens, maybe that was what you meant before, that we can still like directly operate on it. But yeah, let's fix that. So instead of range m, let's start the counting at 16 and then go until the end. Because that way the negative, yeah, okay, thanks. I was just being slow. So let's try Python again and refresh. Okay, it's different. Probably it looks kind of wrong. Since it's supposed to look like this, I think. So what are we doing wrong here? We are looping from 16 to length m. So the thing is that we cannot do, or I mean we can, but with simple logic we cannot operate on the same data multiple times. Like once we have stored index 0 here, if we read index 0, which we do here, for example, no, I mean here, for example, I minus 15, or yeah, but you get what I mean, or here I minus 16, yeah. This is dependent on the output of this state or stage. So I think we can keep it like this, but I'm obviously doing something else wrong. So yeah, we have these additions. Yeah. Isn't the transform one also dependent on the previous elements? Yeah, it is. So this is dependent on this. And then it will sort of initialize index 16 until 64 or 63, which is why this memset isn't technically needed, but it confused me a lot because this is a stack variable. But yeah, I mean in itself. Yeah, so that is very interesting. So let's read the code and see if that is the case. Oh god, you're right, because we're updating mi, but we're only reading. No, you're right. We're reading previous elements. Oh, this is gonna get a... Oh, what a headache. Yeah, you're right. So we are changing the m array, and then we are using that. Yeah. Oh, no, okay, this is... Maybe I should just read a paper. God. So what are we actually doing? Yeah, so we are basically here. So can we do this in a smarter way? Extend the first 16 words into something into the remaining words. Yeah. Um, so I guess what we can do is if we split this up into 16 like we prepare 16 bytes and then we move on. So first we go from 16 to 32, then we go from 32 to 48, and then from 48 to 64. I think that's a way forward at least. So yeah, this is kind of ugly, but whatever. So 16 to 32, 32 to 48, and then 48 to 64. And oh, okay, so what we're doing now instead, we are splitting up the this processing into multiple stages. And here is a typo. No, this whole stage shouldn't be there. Okay. Let's see if this works. Isn't that part still going to wreak havoc if with the I-2 part? So we are writing to 16 and forward, but we are reading somewhere between 0 and 16. So this is dependent on this part. And then this one should only use stuff that is prepared in this step. Let's try it. Oh, it breaks. Here we go. Oh. I think I'm missing something in my head. Like what I don't really understand is how this can produce all of this. Because the only data we have in M is really OX80 here. Am I printing too much? I feel like I'm missing something. All right. No, I'm not thinking clearly today. This is never gonna work because, yeah, I somehow thought that I was only looking at 16 entries and beyond, but I'm looking up until 16 entries. So all of this is dependent on each other. This is never gonna work. Crap. Okay, so how do we do this then in a sane way? Because here we create a long chain of dependencies. Like, yeah, this is gonna be a mess to write. I don't think I have the brain power to do that, honestly. This is a pain. Okay, I think I'm gonna give up. I have to do this in peace and quiet, I think. So I think I'll end this Sha-256 section here and say, well, I need to think a bit more to do this properly. And instead, I'll hop on to the Cha-Cha-20 instead and improve that, because that's something that I at least understand. To be honest, I haven't done any homework at all on the SHA. But I mean, the algorithm doesn't look that difficult. It's just that this is going to end up being a really long dependency chain. And in order to express this in a sane way, I don't know, need to think about that. Then here we have some interesting stuff going on. I mean, the main pain point is that we are operating on outputs in the loop. Like each iteration uses something from perhaps not the previous one, but yeah, a few elements back. So yeah, this is gonna be a pain. So yeah, let's go back to Cha-Cha-20. So okay, let's do some recap. This would then require 48 clock cycles, wouldn't it? Yeah, exactly. Which would be horrible. Like, I mean, I could write that, but I mean, we could actually give it a shot and do do this in a 1 clock per iteration. Yeah, okay. I'm gonna give it a shot now. Let's do it. It's just not gonna be fast. So let's make an expression. Can the design language automatically unroll the loop? I don't think so. Or maybe it can. If anyone knows, please help me out. But what I'm gonna do is I'm gonna generate a state machine, like I did in my other code here. So here I'm generating entries in the state machine, which helps me out. So yeah, I'm gonna do that now. So instead of having the loop out here, we can do a loop here for I in range from 16 to 64, right? And we will create a state called transform I. Yeah, let's do like this. And then we hope to transform 16. Perfect. Yeah, and then instead of doing an array of operations, we're gonna just operate on one single entry. So when we go to number 16, we will update 16 with the dependencies from the previous items. Perfect. And then we have to change the state. m.next equals like so. And then we can add the final transformation stage. Let's just do like this and call it 64 and just stall. Okay, transform A is already defined. What am I missing? There we go. Yeah, okay. So here you can see we get this long chain of stuff going on. But yeah, maybe it's actually correct. Oh no, we got a spammer. I'm gonna kill the spammer. 1 second. How do you do that again? Okay, I think that was it. Okay, so again, here we have, so each iteration is operating and changing something, as you can see here. Let me move this to the other screen, and then we can compare. Okay, so this doesn't look right. It is definitely doing something, but it doesn't seem to be doing the right thing. So Yeah, you're right. So let's see if we can fix that. So one thing that I was thinking is wrong is it might be this one, that we're loading the data in the wrong NDNS. So let's do NDNS swap to 1 and 0 and see if that works. Yeah, it's different. 9B something. Yeah. Oh, look at this. It actually seems to be correct. And here we have 44 BC and so on. Okay, I've looked at 2 entries and I think, yeah, looks good enough. Good enough for me. 22 something. Yeah. Oof. Yeah. Perfect. I think that's a win. So now we can continue. And this is not horrible code. I mean, it doesn't look that horrible. It's still readable, which is good. So let's continue on. Perfect. So we're basically here. Yeah. So what's happening now? Now we're doing another 64-step loop. Oh, so many loops. This time we are only operating. Okay, this is good. We are only operating on a single entry at a time. This is the lookup table, right? Yeah, K64. So we have a lookup table and we have the entry, and all of this is generating temporary variables that is then being stored into the state. So all of these get crunched, and finally, after 64 times, we are storing them. So, right, we're accumulating them. So we cannot reuse the state here because that would mess up the state. So we need to not touch the state and keep these variables separate. So let's do that. Let's do that. So I believe that we can start with doing all of this in one single cycle, and then we do this 64 times. So I'm just gonna borrow this. So yeah, here we go. Transform 64. Perfect. Yeah. So we're gonna need some macros. EP1. I guess all of these macros essentially. So let's just implement them. And also my worry about the addition seems to not be a problem. So we can skip that. So yeah. I think one nice property with this code is that these macros do not write back. Like some code that you look at, for example, the Sha-256, I think, this had macros that changed the variables that you sent in. So that this was a little bit confusing to work with. But this is easier because this is only, it's not changing anything. It's just taking an input and returns an output. So let's just, honestly, I think we can just copy and paste this. Yeah, this should be fine. Perfect. And this is the same thing. Just, yeah, bitwise and bitwise XOR, nothing strange. Yeah, so we rotate right, 2, XOR rotate right 13. So this was simple, almost too simple. So I guess there will be something hard. So I'm gonna copy this because we're doing something similar. We're operating on M, and yeah, so here, yeah, let's think a little bit. So we can create a function that performs all of these steps as an expression in a sort of non-pipelined single. Does this then require 7 adders, or are these plus operations XORs? They are actual adders. So this will be probably stupidly expensive, but once we have a design that we can simulate, we can then optimize it. So yeah, let's break this down a little bit. So to make things easy for ourselves, maybe we should we can just move this up here and call this, like, I don't know, what should we call it? Something interesting. Let's call it transform. Yeah, and it right. So how do we translate this into nMigen? We can skip the loop, of course. How do we write this in a nice way? I don't know. So I'm just gonna do like this. Yeah. I guess you can even... Wait a minute. No. Crap. So this keeps state between the loops, right? Of course. So we need... Right. And here they're actually initializing them to this state. So it's a copy of the state that needs to persist between the loops, right? Yeah, I suppose I should learn and just read first and do later, but I'm kind of eager sometimes. But yeah, let's think here for a little bit. So yeah, we can keep these signals outside of the loop. And we also needed this T1 and T2. Where did they come from? Ah, here. Okay. Cool. So that's T1, T2. I wonder how many cycles this will take. It feels like it's gonna take like 128 cycles or something. I don't know. Anyway, maybe even more. But maybe that's still faster than doing it with the CPU. We can always optimize it later. Okay. So when we get to this step, we should reset. Yeah. So we should reset the variables. Oh, wait a minute. They are words, not. Did I make them words? Yes, I did. Okay, cool. Perfect. Let's just oh, wait a minute. So we have state and we have M. And they are definitely not the same thing. So M is our operating matrix, and the state is what contains the initial data, right? Because the data is loaded there, yeah, and it has been transformed. Okay, now, so we need to load this from the state, and let's just do like this. That way we don't need to do self.state everywhere. Oh. We can do it like that. What about T and H? T1 and T2. Okay, they're being set here. So they're actually not accumulating anything. They are just temporary variables. So I don't actually need them to be persistent. So let's remove them. Let's call it okay. So now we have an initial state. Perfect. then we can move on to the next one. What do we want to do here? This is where we do the actual processing. So now we need to do this. So actually, okay, so we're reusing T1 in two places here. Okay, so I'm gonna create a temporary 32-bit, or two temporary 32-bit signals. Signals can be assigned with in the comp domain, which I mean, I don't know what makes more sense. Maybe I should. So we could either use the expression twice or use comp logic to sort of splice it up to two places. But yeah, we can try this. So t1.eq, this expression, where I is this one. We're gonna do this thing again. But this time we want to loop from 0 to 64. So yeah, here we go. We need the k as well. So I'm just gonna steal that from up here. I'm not really sure how to do this in a sane way. Maybe this would be fine. Or maybe I should wrap them in const. I am not really sure. I could do that like this. I believe this should work. Maybe like this. Yeah. Yeah, okay. So the reason why I do this is that I want to be sure that it's gonna perform like 32-bit operations on it. So maybe it's not needed, but I want to avoid like strange bit issues. So here we have the keys, or the constants. And if I need to endian swap them, I can do that here. Hopefully I don't have to do that. So anyway, there we have them. Perfect. Just cleaning up here a little bit. So yeah, we can remove that. Then we need T2 as well. convenient that C and Python actually is not too far away. Can almost copy and paste code. Okay, so since I'm using comp here, I'm actually allowed to use these variables in the sync assignments because they are, when we enter this state, they will be connected. So let's do that. So we want to translate this into nMigen code. Actually, I'm not. Depends on how lazy you are. Sometimes you can be super lazy and do some fancy stuff. I'm just worried I'm gonna make some copy paste error here. HGGF FE EDT1 D. So do we have any dependencies here? No. So what I was slightly afraid of is that the order of this in C code matters, but the order here doesn't matter. We're reading and writing. So yeah, let's see if this works. So again, we are looping 64 times. We are calling it transform. All right, we need a next. We need something like this. Then we have the final transform 3 here, right? Where I think we just write it back to the state. So basically this in reverse. There you go. Yeah, okay. So let's see if this compiles. Yeah. Just write back. Looks more like perform even one more. Oh, sorry. You are right. Damn it. Thanks. That's actually really helpful. There we go. And this should overflow as well, right? Yes. Perfect. Okay, so let's see what's happening here. Line 1, 2, 3. Okay. Save yourself the pain and rename those to R0 to R7. Yeah, you're right. I'm just, yeah. Maybe in a cleanup later. Okay, let's see here what's happening. Transform 164 is referenced but not defined. Oh, right. I did some rewrite in the blind. Right. Thanks. Okay, 264. Okay, I probably have the same bug here. And there we go. Okay, this is going to be interesting. This is going to be really interesting. So I I think I'm missing something. So we are actually entering this transformation state. Yeah, transform to. Oh my god, I'm gonna need to simulate some more. Let's do like that. Okay, so there it's done. But it looks like nothing is changing really. So yeah, already here nothing is changing. So we are going from transform 1 to transform 2 to 0 to 1 to 2. Okay, so why is nothing happening? Did I forget something? Um, mm, so it's a little bit slightly annoying here that these variables are not showing up here. But yeah, I'm gonna take you up on that and rename them to R0 to R7, I guess. So this is like an nMigen question. I have these signals here that I'm using and doing stuff with. Why don't they show up here? I don't know really how to do that. The way I usually do it is to expose them somehow by putting them in the self. So let's do that. Are these signals then implemented as registers? Yes, that's correct. So the funny thing with nMigen is that when you operate in the synchronous domain and do some kind of signal equals something, then this will generate a clocked statement and will turn this signal into a register. But if you don't, for example, like we do here, these will be wires basically in Verilog. At least that's my understanding. So yeah. But yeah, I need to sort of expose these somehow. So let's do like this and create 8 registers and then do like this. Let me just move that. And then we can do like this instead. Oh no, alphabet. I'm sure I'm gonna mess this up. looks good. Yep. You can do m.d.sync plus equals. Oh, yeah. Thanks. Here, right. Gonna copy and paste. Thanks. All right, that's the one above here, right? Yep. And then here we just do the reverse. All right, and the accumulation. Almost did the same mistake twice. Shame on me. Yeah, there we go. That should be it. Whoa, it actually worked. Okay. Let's see if we can replace all signals. Perfect. Okay, this looks a little bit interesting. We have a lot of signals. A lot. Holy shit. So where did R go? R? Oh, I need to name it. Forgot about that. There we go. Reload, and there we go. Yeah, here we have the R variables. Perfect. Okay, so where are we? We should. Right, so that is the hash output. State. So that is the final transformation. That is basically this part. And then after the final transformation, we are just copying the state and doing byte swapping and putting it back into the hash, right? So basically this should be here somewhere. We should see the hash here somewhere. I guess in the state. Or wait a minute. Yeah, because we did this part. So the state should contain the hash. Yeah. Okay, I'm gonna name it. 1 second. Oh. Right, so here we have the state, the output state. So why is it keeping on changing in the end? That's no good. So it seems the state machine, all right, it ends up accumulating forever. So let's do like this. And then we should copy, let's see here, hash. Did I save that? We have the output hash, right? Let's do like that. Hash I equals state. we're gonna replicate this basically. So oh god, what is happening here? Ah, okay, now I see. It's just byte swapping it. So but yeah, here I have it as bytes. Yeah, let's do that soon. Now I just want the state machine to sort of finish. Oh, final is already defined. Okay. Okay. What should we call this? Prepare final. Okay, here we go. So let's see if we can recognize this from the actual hash. E3, B0, C4, 4, 2. Yeah, look at this. This is the actual hash. Perfect. Yeah. So anyway, I think as a stream, I think we managed to get somewhere. Now we have the initial empty hash state output here. Perfect. And obviously this is far from complete. We need to basically run through this whole horrible mess for each block that we want to update the hash with. So basically this step should reuse all of these steps for each data block that we are loading, like this part here. So what we're doing, what this code is doing here is it's preparing the data and it's running the whole transformation for each block. And we need to do the same thing. So yeah, let's try to synthesize this on actual hardware and see what kind of horrible performance we get. So obviously it's not done, but we're actually performing all of the important steps. How does the, oh my god, how does the generated Verilog source look? Yes, okay. Prepare your eyes. Here we go. Oh, only 3,000 lines of stuff. Yeah, well, here we go. Don't tell, don't ask. Yeah. The good thing is that if there is a bug in, yeah, if you for some reason need the Verilog, you can actually follow this. So you can see that, oh, this random variable is actually a product of this specific line in the Python code, which is super useful. Not that bad. MATLAB produces worse stuff. All right, if you say so. Yeah, perfect. So yeah, let's make some hardware. So I'm gonna reuse the Sha-256 that I did just before. Just gonna copy and paste, call this like that. So I have this framework set up since before. And let's see how it works. Oh no. Aha, Streamlabs. Okay. Oh, yeah, well, sorry. I haven't fixed the bot. Anyway. Okay, let's go here. Yeah, let's just clean up. Okay, so this is a super simple top-level design where we instantiate the hash implementation, and then we should also so this statement here will tell the hashing engine to start, and then we connect the LEDs of my physical FPGA to the output hash. So the idea is that this should make sure that all of the signals are sort of used, which they are not really, but I don't think it's going to be a problem. Usually when you have a complex state machine, the tools don't optimize it away. At least that's been my experience. So let's see if I can try it out. All right, I need to fix some names. Copy and paste is fun, but yeah, if you're lazy, you're lazy. There we go. Okay, so let's see how it goes. Did it already finish? Something seems off. Shouldn't be this fast. Yeah, you're right. So I'm doing something. Yeah, I think actually the tool managed to figure out that we're actually not using the output. So let's do that then. So I suppose we need to do something like this. Does this make sense? No, I need to do like this, right? Okay, I believe it's the Yosis stage that takes some time now. It's definitely taking longer time. Oh, and it's 12,000 lines now. Okay, so I'm not sure what we looked at before. Maybe it was the Sha-256. I don't know. Oh my god. Oh goodness. Okay, it's still working. Starting to get slightly worried now. So I think this is the old output. Oh god. Oh goodness. Is it 113,000? Yes. 113,000 lines. Holy crap. Sorry if you already said it, but for which FPGA board are you compiling? Okay, an ECP5 board that I made. So it failed because something is horribly wrong. So I guess I have some expression that's just stupidly long or something. Oh, look at this. It's only using 91%. So I'm probably doing something extremely stupid here somewhere. So I wonder. Oh, look at this, 102%. So, okay. So technically it should fit, but practically it does not, I suppose. Okay. So, yeah. Okay, I have a solution. We upgrade the FPGA. We just magically upgrade it. Let's just upgrade it to 45K loot variant instead. So now we have twice as many loots, but I don't actually have the hardware. Or I do on another board, but yeah, this is just for testing. But yeah, I'm obviously doing something really stupid somewhere. So I don't know really. Could it be my use of arrays that sort of end up becoming horribly expensive to do? Because I think arrays, the difference between an array and a list is that an array can be indexed by a signal. So I think in all of the cases here, I'm using a variable, like a compile timed variable to index. So I don't actually need them to be arrays. And I think arrays have extra costs to them. So, but yeah, let's just see if it finishes. It would be fun to just see if it, what we did on stream actually could run on hardware. But yeah, this is probably gonna take a while. So while that is running, so I think that it's already produced its output. We can sort of work in parallel and try to figure out what is it that is causing this enormous resource use. So I mean, obviously we're doing a lot of stuff, but maybe we can avoid like this part here. This is super important, of course. But we do this whole implementation 64 times. So what we could do is to have this as sort of a compute block, or whatever you want to call it, so that this sort of network of logic is instantiated once, and then we feed different inputs and outputs to it. That way I assume that this logic will be replicated 64 times, which is probably the reason why this is taking quite a while. Yeah. Oh, look at this. So now with the bigger FPGA, we're using 56%. And it's routing. Oh, look at this, 26 megahertz. Oh, that is slow. But fortunately, it passes our 16 megahertz clock. Perfect. Okay. This is fun. So now it's actually doing the routing. So we should be able to find the longest chain of logic. the offender, if you want. And I'm guessing that it's something here, but it doesn't have to be. But yeah, I mean, here we have the, oh my god, could it be that it replicates the lookup table 64 times as well? No, it doesn't. It shouldn't, because I is this I. So I guess the lut values will be sort of put into place for each, like each value in the lookup table will be instantiated for the corresponding iteration of the transform. So that is probably not the problem. And mi is just a reference to the m. Yeah, it will be connected. Honestly, I don't know. It will be interesting to see like how many things am I doing wrong here? Probably a lot. But yeah, still, it's not a lot of code. Like if we just look at lines of code, we have this state machine which generates states. Like how many lines is this? That's like it doesn't show, but yeah, around 100 lines of code. Of course, it's not finished yet because we don't do the update stuff. But this shouldn't be too hard to do. Like here we can have some logic that does the padding properly, or we can just assume that the user will pad it correctly. And then we can just reuse this whole, we can have like a different final step. Like here, we can have like, is this the final step or is it just an update step? And then we can sort of jump back into the state machine and reuse all of this logic. That should be fine. Yeah. Okay, it's still working. Still working. Yeah, placing and routing. It is what it is. But usually, I mean, I've obviously done something quite aggressive here. I'm sure you can do this way smarter. This is just a really, really naive approach, basically converting procedural code into a state machine. Oh, that's the wrong file. But yeah, let's see how it goes. Still working. Okay, still working. So honestly, I don't really understand how this works. So I suppose this is the number of LUTs that the logic needs, and then it is applied to the physical slices that we have on the FPGA in question. And then we somehow need to work out how to connect everything together. And maybe there is not even a possible way. Like even if you're using less than 100%, maybe it's not possible to route. I don't know. So anyway, it would be interesting to understand a little bit more about how this works. But like already here, we know the max frequency of 26 megahertz, but then it's getting optimized, I think, and we might get a faster fmax. But yeah, I'm not really sure how long this will take or how many iterations it will run for. Like, what is it that, what's the exit condition of this work? Is it remaining arcs, right? Okay, so this is probably, it's working It's trying to get this one down to 0. So, okay, so maybe that is the problem, that I have so much routing that it's really difficult to route. I believe that's the problem. I don't know. 64,000 arcs. Anyway, so I still think it was an interesting session to have. We actually managed to get somewhere. Here is the actual hash of an empty string, but still, it's still something. We have implemented the basic components of the hashing algorithm. So yeah, I think it's something. But yeah, obviously it's not very optimal. Still working. So I'm thinking of bailing out, because this will probably take forever, and even if it finishes, it will probably not be very useful. Like, it doesn't do anything. But yeah, so I think we need to improve this quite a lot. Did I just arrive at the end of the stream? Well, Funka, welcome. Yeah, sort of, I guess. The final frequency might be interesting. Yeah, sure. Anyways, don't know if you said, as I had to run for a while, but couldn't you save a ton of loots by having a counter in the transform 2 state instead of having 64 states and duplicate logic? Yeah, so that's really interesting. So, going back to the whole question about array. So array allows you to access a specific array element using signals, which is something that I usually avoid, because you end up having to have a mux for all of the indexes. So maybe that is actually what we should do. So maybe we should keep it as an array, and then instead of unrolling the loop like this, we should stay in the state and iterate over a variable instead. So we can actually try that. So before I'm gonna destroy all the code, I'm just gonna commit this. So because this is still, even if it sucks, it's sort of working. So I'm just gonna add the code. I got a bunch of crap as well. But yeah, I think this is it. Yep. Like so. So yeah, that's a really good suggestion, Jens. So I guess we can start with something simple. And because now we have sort of a unit test, because we can start with turning this into a unit test. So let's add a signal. So here we create a signal called already, which we can use to tell to the outside world that we are done. Like so. And let's just do this once. We can of course improve this. Funka, don't worry. We have some stuff more. We have still some more stuff that we can do. So I can just do a really quick recap. So I implemented the SHA-256 algorithm on stream, and the code is not very good. It's very expensive and it's slow, but we can see that the hash it produces of an empty string, empty data, is actually correct. This is the same value that you get if you use the proper algorithm on an empty string. So, like this is what you get from an empty string. And now we're doing some slight optimization, so we're trying to make it a little bit better. And yeah, so let's do like this. If so, it's a little bit of a funny syntax when you use this whole simulation thing. But yeah, what I'm doing is I'm getting a value out from the simulation, and this is one way to do it. I'm sure there are different ways to do it, but yeah. So, all right. So let's just see if I can run this unit test. Yeah, okay. So what I'm doing now is that I'm looping until I get the O ready, and then I print done, and I break out of the loop and run for a few more clock cycles. Why don't I get the print anymore? Uh, let's do like this instead. Okay. Not really quite sure what's going on here. So for some reason, I'm only simulating a few. All right, I forgot the most important thing. So you need to run yield like this without a statement in order to simulate a clock cycle. Yeah, okay, so here we go. Yeah, okay, this makes way more sense. Now I can. So just to recap what I'm doing here, this is the main simulation loop. So first we run one clock cycle, we enable the data ready flag, which tells the engine to start processing. Then I can remove those. Then we loop for up to 300 times. And if the already flag, which we set up here, is true, then we are done and we break out of this loop and we simulate a few more clock cycles and we're done. But what we can do now is that we can actually verify the output of the hash. All right, this is because O-hash is what's it called again? Array. Yeah. Okay. So this will be a little bit interesting. Hmm. We can do like this. I always forget the length of this one. 32 bytes. Okay. 32. So we save the output into an array, and then we can print it. And instead of doing like that, we can do yeah, what's the best way? Why do you require yield? Hold on, what would happen if you used if yeah, okay, so actually that's a really good question, and it's about nMigen internals that I am not really comfortable. I don't really understand how it works beneath the hood, but this whole process thing is some asynchronous iterator thing, Python magic, and I just know that this is one way to access data from the simulation into the function. And yeah, if I do this, it will not work because I think this is sort of a compile time if statement. And here it will generate sort of a, yeah, some Python magic so that it becomes sequential, I think. But yeah, this is not really, I don't really understand how it works. But yeah, it's all part of the simulator stuff, which is magic to me. But it works, and it's fun. So now I'm just gonna write some stupid Python here to print this as hex. Yeah, I'm feeling my brain getting tired. So I guess I can do like yeah, I'm feeling my brain is empty. I forgot how to turn stuff into hex. God damn it. So I guess one way to do it is to just do like this. Yeah. And then I can do yeah, that's one way. But I think if you have a leading zero, it will not be so nice. Let's do like this. Is it like that? Yeah, there you go. And as you can see, this one is inverted. Oh, nice. Pythonic ninjas. So let me see if I can. Anyway, it might be possible to do it like that, but the whole yield thing, so this would essentially become a value, but then to iterate, like the whole yield thing and the iterator is really confusing to me. Like if you try to do like some fancy magic, like with a list operator and so on, yeah, I usually end up just writing simple code instead. So let's just see if this is correct. So here we are in the final one. It should be E3 something. Yeah. So here we see that it's big endian, little endian swapped. So let's swap it. Try again. Yay, look at that. Yep, it is correct. Perfect. So is it still synth? Yeah, it is. It is. Yep. So actually, this time let's what's the proper way to do a SHA? Yeah, here we go. Perfect. So let's start with a sort of known known correct. So if we skip the update part and just digest, and then how do we get the output? Right. Okay, move this down here. Oh. Okay. Yeah, so I'm gonna assert this equals this. Perfect. So this is the proof that it works. We can use the Python's built-in stuff and ensure that it's correct. Perfect. And yes, it is still synthesizing. So asserting nothing. Yeah, it seems it seems that way. Yeah. Okay. Huh. Aha, okay. Is that how you write it? Oh, wait a minute. But wait a minute. You shouldn't use assert. You should use the other thing, which I forgot about. This one. There you go. But yeah, it's it works. So if we actually have some data, we see that, oh, look at this, there's a difference. So again, now we have a test. We can also have So 120 cycles and using all of the. Oh my god! Oh, it's getting closer. Only 9,000 whatever left. Oh my god! Yeah. Horrible, horrible, horrible. But anyway, so our implementation takes 120 cycles per hash, and it runs at, what was it, 20 megahertz. So yeah, 26 megahertz. Divided by 120. So we have 200,000 hashes per second. Yeah. Holy crap. Yeah, exactly. But yeah, I'm probably doing something extremely stupid here that ends up eating all of the resources. I mean, the fact that I can't put my finger on it, I mean, it's probably that this logic is being replicated 64 times and this logic is being replicated 64 times or 56. So we can most likely improve this a lot by doing what Jens said before. What would happen with SHA-3 512? Yeah, who knows? Who knows? I haven't even looked at the algorithm. But I was really surprised with the Cha-256. It was really, really nice to implement. Like I can show you here. So this is like the meat of the algorithm, the whole add XOR rotate, add XOR rotate. And this can probably be written way, way cleaner, but this is how I did. So this is the so-called quarter round. And then yeah, you have this 16-word state that everything, so you operate on a 16 like 4x4 matrix of 32-bit words, and you load it with some magic numbers that are not really secret, not strange numbers, just like some text, and your key, a counter, and an IV, or nonce, whatever you want to call it. You load it, and then you run 20 times. So here I have implemented it using a proper state machine. So here it's actually only 2 states, and then I loop. And then finally we just do some final addition, and that's it. So this one is actually being synthesized quite well. So it uses 1500 slices, so I'm getting almost 1300 megabit per second throughput. But the SHA, yeah, this is like, because I was basing it off this very sequential code, I ended up duplicating the logic many, many, many times. But again, I think we can do better. We can just improve it. But I wanted to have like a basic baseline before optimizing it. So yeah, I think that's what we have now. Regarding the Cha-256, 60 megahertz and how many clock cycles? So I think it was, so I made a couple of implementations, 23 clock cycles. It's not 1 gigabyte, it's 1 gigabit. So it's like 100 and something, 158 megabyte per second. So it's not like magically fast, but it's only using 1500 slices, which is like 10% of the smallest ECP5. So this is way more useful than what we built today. Yes, I made a different implementation. Would it fit? Oh, interesting. I mean, if I remember correctly, an ECP5 slice contains 2 LUTs per slice. So this is basically 3000 LUTs. So on a 1K, probably not, but on an 8K, probably, or quite likely. So for example, the one that's being used in the Glasgow. So if you, I have no idea about the speed though, but it would be an interesting thing to try out. See if Glasgow can do Cha-Cha-20 in real time. So I got like 60, 65 megahertz on the ESP5. So I have no idea what kind of speed to expect on the Glasgow or the UP5. Is it the UP5K or 8K? I don't remember. I think revision B used 5K and revision C used UP, or I don't remember honestly. Let's check it out. Yeah, it's using the 8K. So yeah, that should be enough. Should be enough. So I'm not really sure what you would use it for, but well, now we have some IP. Why not? And yes, this is still running. Holy crap. Will it ever finish? Will the boat, you know, get free in the canal before or after? Okay, I think I'm gonna call it quits here. But we can still commit the changes that we did. Yes, it's not worth waiting for it. So let's skip it. Why did I remove this file? Can't remember. Anyway, this one we should add. Okay. So yeah, I guess we can try to optimize it because now we have a unit test that actually checks stuff. So let's start with this loop here. I guess that is the sane, simple thing to improve on. So let's create a counter. Let's just keep it 8 bits, simple that way. And then we initialize it as 0. There we go. I suppose 16. And then instead of having a for loop here, we are going to use the counter here. And then also count it up. then we need to rewrite this. m.if. So this might look a little bit strange, but whenever you are using, actually this is not used. If counter equals 63. Here we go. So what I was gonna say is, whenever you have if cases that are handling signals, like not variables, normal Python variables, you need to use the m.if. Investing more adders to have fewer adders. Yeah, exactly. Yeah, so anyway, if we are at the last counting step, we want to move on to this step. So let's just see if it works. No, it did not. Okay, crap. I'm still using I somewhere. Where? I don't see it. Oh, here we go. Okay. Oh, look at that. It worked. So now we probably have optimized, like, yeah, optimized it a lot. So let's do the same thing in this stage. Instead of looping like this, we should do like this. And no, 0. And then in the sync, we iterate. And then we do the same thing here. Just okay. Now I did some mistake. Right. So we need. Okay. I guess we can try this. Okay, it worked. Okay. Let's synthesize one more time. Okay. Let's see what happens this time. So we have removed our duplication of logic, and we have verified that it actually works. So that's a huge win. Now we're waiting for the uses and everything else to churn through. So yeah, this is the output from the previous run. So I believe uses is running and compiling, working hard. Yeah, so we have the same amount of cycles, but way fewer states. As you can see here, we go here from idle, update, prepare final, transform 1, transform 3. Yeah, it's way fewer states. But it seems that Yosis still takes a lot of time. Or actually, it's Python. What the hell? Python is using a lot of CPU. I believe I might have triggered some edge case in nMigen so that it uses tons of CPU right now. Usually that's not the case. Usually the nMigen stuff is very fast and generates the IL and so on. And so what is? Oh my goodness! Oh my! Oh! Wow! What is this? So I pressed Control C, and this is the call stack. Jesus Christ! What's going on? It's the array proxy stuff. So because the lookup table is huge, this lookup table stuff. So maybe I should convert this into a memory instead. I don't know. Does it make sense? So let's just ignore the k for now, just to try it. So I'm just gonna remove the k part in the equation and see if it synthesizes insane amount of time. It's still Python that takes CPU. It hasn't really generated any files yet. It's still just running Python to try to make sense of what I've done here. So I wonder, what is it that takes such time? Line 88. Yeah. So I don't know. It seems that it's very, your synthesis tool should normally automatically be able to convert it to a memory. I think that is only true if you use it as a memory. Like if you have a data enable and so on. At least that's been my experience. But you're probably right. But it could also be that the nMigen stuff makes this like it operates on quite low level. So maybe I'm asking it to actually not implement it as a memory by doing it like this, because I could use a memory instead, which lets me. Let's see here. Oh, nice. I've been playing with the ESP5 and nMigen too. I'll have to rewatch the beginning of the stream. Yeah, go ahead. I'll be uploading it to YouTube as well. But yeah, most of it has been me just scratching my head and cursing almost. But we ended up implementing all of the code needed to produce the hash of an empty string. So at least we came that far. So now we're trying to synthesize it for a hardware, and it's simply not working because I'm doing too much are you going to try and integrate your course into an SSE? Yeah, what I have here is a sort of a playground project where I have applets that use different IP that I've been creating over the time that I've been playing around with FPGAs. And I would like to move out like actual useful stuff and create a library with sort of useful libraries. For example, the HDMI or DVI-D stuff and VGA and so on, which is kind of nice to have. And integrate it into, for example, a LightX project where you can have like a RISC-V CPU and then expose a peripheral, for example, with the hashing or whatever. So yeah, currently all of this is like really sandbox playground crappy level. Like it's not meant to be used. It's just a learning exercise for me. But anyway, it's fun. So right now I'm trying to get get my code to actually synthesize, and I'm able to run the simulation. Well, not right now because I changed some stuff. But yeah, here we can see I made a unit test down here where we create a hash of an empty, like non-zero data, the initial state basically, and we assert that yes, we do produce the same hash. So yeah. And then I tried to synthesize the code previously, and we ended up using basically all of the LUTs inside of the FPGA, and place and route took forever, literally forever. So we gave up on that and tried to optimize the code a little bit. So now it should produce smaller or fewer LUTs. However, for some reason, the synthesis or nMigen is taking forever to actually finish, which is normally not the case. Usually, nMigen is super fast. Like it takes less than a second to produce the Yosus or the IL that is being fed into Yosus, which is then being producing the files needed for the place and route that NextPNR is using. And then finally, you get a bit stream. And normally, this takes no time at all. Like just to give you an example, I'm gonna build the Sha-256 implementation. It takes a while because it's doing a little bit of complicated stuff, but here it's running NextPNR, and like this is a quite simple design. It's only using 1500 slices, but yeah, here we are done. And we have our timing report, and we get our max frequency, 63 megahertz. So that works really well. But yeah, for some reason, which is probably because of the whole array stuff, I should probably use a memory instead. But that will also limit me to the speed of the internal SRAM, which is not super fast in the ECP5. However, it might be the proper tool for the task at hand. Yeah, I don't know. I think I'm getting a little bit tired now. I'm gonna stop the stream. But thanks everyone for joining. It's been fun. I've learned some stuff, and I hope you have learned something too. So yeah, see you next time. I'm not sure when, but I will probably tweet something and yeah, do a stream again. It's always fun. So yeah, see you next time.